Imagine training a large language model that doesn't just follow generic rules, but truly understands you. Not just your tone, your style, or your preferences, but the uncertainty behind them. That's the future of personalized AI. And today, we're diving deep into a breakthrough framework called Variational Reward Factorization, VRF, a new way to make LLMs not just smart, but sensitive to individual users. Let's start with a problem most people overlook. Personalization isn't just about matching preferences, it's about modeling doubt. Right now, most personalized reward models treat each user like a fixed point. They take a few interactions, crunch the data, and spit out a single best weight vector, like a user's preferences are certain, stable, and perfectly known. But in reality, human preferences are messy. They shift. They're inconsistent. They're uncertain. Take two users. User A gives consistent feedback, always prefers concise, factual answers. Their weight vector is tight, confident. But user B, they bounce between formal, empathetic, and casual tones. Their preferences are diverse. Their signal is noisy. And yet most models treat them the same, assigning equal confidence to both. That's a fundamental flaw. This is the core insight behind VRF. We shouldn't represent users as points. We should represent them as distributions. Let's break it down. Hash the problem: two hidden flaws in reward factorization. Reward factorization is a powerful idea. It decomposes a reward into shared basis functions, each capturing a distinct preference style like formality, empathy, or conciseness, and user-specific weights that blend these styles. But existing methods suffer from two silent failures. 1. Isolated preference modeling. Each user is modeled in isolation. Even if everyone shares common patterns, like valuing clarity or empathy, the system ignores that. It's like asking someone to learn a language without ever hearing others speak it. 2. Deterministic point estimates. Even when data is scarce, models still output a single number. But that number carries no uncertainty. It doesn't say, "I'm not sure," it pretends to know. And that's dangerous. Because when a model is wrong, and it will be wrong with limited data, it doesn't know it's wrong. It just amplifies noise. Hash the solution: Variational Reward Factorization, VRF. VRF flips this entire paradigm. Instead of estimating a single weight vector for each user, it learns a variational distribution, a Gaussian, over a shared preference space. So now each user is not a point, but a cloud of possible preferences. Here's how it works. Step 1, variational user encoding. Given a small reference set, just a few interactions, VRF uses a neural encoder to process each preference pair. It extracts hidden states from the LLM, computes differences and averages, and maps them into a latent space. Then, instead of averaging all signals, it uses the product-of-Gaussians to aggregate them. This isn't just a mean, it's precision-weighted. More confident observations pull the distribution closer. More uncertainty spreads it out. So if a user has only 3 interactions, their distribution is wide. If they've interacted 50 times with consistent feedback, it's narrow. This is uncertainty quantification from the ground up. Step 2, probabilistic preference bases. Now the system learns K shared preference bases, each a Gaussian in the same latent space. These aren't fixed. They're learned during training to capture diverse, population-level styles, factual, empathetic, structured, concise, and so on. But here's the key innovation. Matching isn't about location alone. It's about distributional alignment. VRF computes the squared 2 Wasserstein distance between a user's distribution and each base. This metric considers both the center preference direction and the spread uncertainty. It's symmetric. It respects geometry. It's perfect for this task. Then it derives the user's weights via a softmax over these distances. The more aligned a user is with a base, both in direction and confidence, the higher their weight. So a user who's uncertain across multiple styles, their weights are diffuse. A user who's clearly formal, their weight is sharply peaked. This is uncertainty-aware preference matching. Step 3, variance-attenuated training. Even with probabilistic matching, training can still be brittle. So VRF introduces a variance-attenuated Bradley-Terry loss. Traditional BT loss assumes a single scalar reward difference. But VRF models that difference as a Gaussian, because user weights are distributions, and the reward is a weighted sum of basis functions. So the reward difference becomes a random variable with mean mu and variance sigma 2. The probability of preferring one response over another is now an expectation, E. This expectation doesn't have a closed form, but we use Mackay's approximation to derive a tractable, differentiable loss. And here's the magic. When uncertainty is high, sigma 2 is large, the gradient shrinks. The model learns to downweight ambiguous signals. It doesn't overfit to noisy feedback. It says, "I'm not sure, so I'll trust this less." This is robustness by design. Step 4, few-shot inference for unseen users. Now imagine a new user, someone you've never seen before. No history. No data. Can you personalize for them? Yes. And it's lightning fast. VRF uses the same variational encoder. It processes the user's first few interactions, infers their distribution, derives their weights via Wasserstein matching, and computes a personalized reward, all in a single forward pass. No gradient updates. No optimization. No iteration. Compare that to baseline methods like PAL or VRF, which require hundreds of steps of fine-tuning per user. At scale, millions of users, this difference isn't just academic. It's operational. VRF completes personalization in under a second per user. That's practical. That's deployable. Real-world performance, why it matters. We tested VRF on 3 major benchmarks: personal LLM, TL, DR, and Prism. Across all datasets, seen and unseen users, low and high data scarcity, varying levels of preference diversity, VRF outperformed all baselines. On Prism, the real-world dataset with crowdworker conversations, VRF achieved 62.1% accuracy for unseen users. The next best method, just 59.6%. But the real story isn't just the numbers. It's the robustness. Few-shot adaptation. Even with just one reference interaction, VRF outperformed the best competitor by 1.9%. That's game-changing for cold start personalization. Uncertainty robustness, users with high uncertainty. VRF still wins, because it knows when it's unsure and adapts accordingly. Downstream alignment, we ran best-of-n sampling. VRF selected responses beat the baseline in 92% of cases, even with minimal user history. And efficiency, VRF's per user adaptation time was 0.6 milliseconds. VRF, over 100 milliseconds. At scale, that's 30 hours versus under 10 minutes. Ablation study, what makes it work? We tested every component. Remove the variance-attenuated loss. Accuracy dropped by 3.6%. Why? Without uncertainty-aware training, the model overreacts to noise. Remove basis separation, LSEP. Performance fell on diverse datasets. The model couldn't disentangle distinct styles. Replace the product-of-Gaussians with simple averaging. Performance dropped. Uncertainty-aware aggregation matters. Use a standard N, 0, I prior instead of a mixture of Gaussians. Accuracy dropped. Regularizing users within the learned space is critical. Each piece is essential. Together they form a system that's not just accurate, but resilient. Case study, what does the preference space look like? On Prism, VRF learned 8 preference bases. Let's visualize them. P1, conversational and natural. P2, thorough and genuine. P3, nuanced and impartial. P4, direct and structured. P7, factual and clear. P8, empathetic and principled. Now look at 4 users. User A, 19 interactions, tight ellipse near P7. Confident, consistent. User B, 3 interactions, wide ellipse near P4. Uncertain but directionally clear. User C, 10 interactions, spreads across 5 bases. Diverse, ambiguous. User D, 10 interactions, between P4 and P8. Moderate uncertainty. The model didn't guess. It learned where people are and how sure they are. The big picture. This isn't just another tweak to reward modeling. It's a paradigm shift. VRF solves 2 deep problems. C1, isolated preference modeling right arrow by sharing a population-level preference space. C2, deterministic point estimates right arrow by representing users and bases as distributions. It's uncertainty-aware by design. It's scalable. It's efficient. And it's robust. And the implications go beyond reward modeling. This framework can power personalized alignment in real time, adaptive chatbots, ethical AI assistants, and even personalized education systems, where understanding a student's uncertainty is as important as their answers. Final thoughts. We've long treated personalization as a matter of fitting data. But real users aren't data points. They're processes. They evolve. They hesitate. They chain. VRF doesn't just personalize. It understands. And in a world where AI is becoming more human-like, the most human thing we can do is to acknowledge doubt. So the next time you interact with a personalized AI, ask yourself, does it know when it's unsure? Because if it does, it's not just smart. It's wise. And that's the future of alignment. Thanks for watching. If you found this deep dive valuable, hit like, subscribe, and share with anyone building the next generation of personal AI.